So, we are back again on this topic ultrasonic testing, and today we will see some applications, but before that let me also talk a little bit about what kind of displays you can see in ultrasonic testing. There are 2 or 3 different types of displays that can be shown on the screen, and depending on the requirement one of these displays can be chosen. The most commonly used display is in terms of the amplitude and the time that we have been seeing so far, and that particular display or that particular scan is known as A scan. But there are 2 more which are known as B scan and C scan. Okay. So, let us talk about them also and see how they look like. So, as I said, this A scan we have already seen, which is a display like this, amplitude plotted against time or depth, and you see the signal in terms of a deflection of the time base or a peak like this. Okay. So, this is A scan. So, this is a one dimensional view of the defects. Then you have B scan. And in this case, this gives you a 2D profile of the defects, and this display is basically an imaginary section through the sample, wherein you can see both the back and front surface, and you will see at what depth the defects are lying when the defect echo appears on the display. Okay. So, that is how it generates that 2D profile of the defect. Okay. So, this is what it is, and if you look at the displays, the display will be like this. So, the time or depth in this case now will be in the y axis, because as I told, the depth will be directly shown on the display, and this x axis now will be scan distance. Okay. So, this will be shown on a fluorescent screen, and you will see the defect echoes as fluorescing points coming into the display and staying there for some time, so that you have enough time to see and visualize them. So, let us say if you have a sample like this, and you have 2 defects at 2 different depths, and now you have taken this probe and you are moving the probe on the surface. So, the moment it goes over these defects, then you will see them coming in this display at that particular depth like this. Okay. Because as I said, this is an imaginary section through the sample where you can see the depth, where you can see both the front face and the back face, or you can see the depth. Okay. So, these will come as fluorescent points on a phosphor screen, Okay. So, instead of the oscilloscope screen that you have in case of A scan. In this case, you have a phosphor screen where these defects signals will come and fluoresce at the particular depth where the defect is lying. Okay. So, this is how the display is in this case, in the case of B scan, and the other one, the next one is C scan. And in this case, you have plant type 2D view of the defects. And in order to generate that, this has to be plotted either on an XY plotter. So, the data is recorded by an XY plotter, or it can be also shown on a computer screen. Which is superimposed on the plan view of the sample. Okay. So, you record the data and then either you can plot it on XY plotter, or you can show it on a screen which will be superimposed on the plan view, and that is how this plant type view will be generated. But in order to create that, in this case the data has to be recorded as a function of each of the reflecting interfaces, unlike the previous cases where you simply send the ultrasonic beam and get an echo from defects or from the other surfaces. In this case, you need to collect the echoes as a function of the position of the reflecting interface. Okay. And in order to do that, you need to move the probe in a particular fashion like this. So, let us say there is a defect on this sample. So, this is the side view of the sample, and the top view is something like this. So, in order to generate that plant type view of the defects, you need to collect the data, as I said, as a function of the position of each of the reflecting interfaces. And in order to do that, you have to do the scan following a particular pattern like this. Okay. So, you have to go like this in a zigzag manner. Like this. And so on. Okay. So, if this defect, if you see the 2D view, it may be something like this. Okay. And now, since you have collected the echoes as a function of each of these reflecting points, okay, you will see a 2D type of view in the display when it is finally displayed on the system. Okay. So, this is the C scan view, this is how it will look like. So, it will show that top view of the plan view, and you will see a profile of this defect at that particular location. Okay. Okay. So, as I said, in this case the echoes are collected, recorded as a function of position of each reflecting interface. And with that you will get a scan and a view like this. Okay. So, these are the different types of scans or views, displays in case of ultrasonic testing. Now, we are going to see a very useful application of this particular technique, which is for inspecting the welds. Okay. Welding and NDT, they go like hand in gloves. Okay. Whenever you do a welding process, it is followed by NDT, so that you find out if the weld is sound or not, if there is any welding defect or not. Okay. And many times you would have seen a welding joint like this, okay, where these two plates are joined across. So, this is the weld, okay, and if you see the view, so this is across this interface, okay, these two plates are joined. Okay. So, this will be the weld. Okay. So, in this case, as you would have realized, you cannot use a normal probe, because in that case it will simply go like this. Even if you keep it on the top of this, there are these surfaces, the welding joint is here. So, it is not appropriate to use normal probe in this case. Okay. So, what we need to do in this case, we need to use an angle probe, so that you would be able to inspect these surfaces like this. Okay. So, when you have a scenario like this, where it is sent at a particular angle, what is going to happen is this is going to reflect back and forth like this. So, first it will reflect from the back wall, and then it is again go to the top surface, and then again come back like this, and so on. Okay. So, that means that back wall echo that you see in case of a normal probe, you are not going to see that in this case. Okay. So, this echo will come back only when it encounters an interface which could be a discontinuity or a defect. So, when it encounters an interface, a reflecting interface, then it is going to reverse the direction and follow the same path, and will come back to the probe, and that is where you get an echo from a discontinuity which is present in the path of this beam, which is going in a zigzag manner like this because of that incident angle. Okay. So, that means in this case, as I said, you do not have the back wall which we have used in case of normal probe as the reference. Okay. So, if you remember, our reference was always this back wall signal. This was the initial pulse and this was the back wall. And we use this back wall as the reference, and we said that anything coming before the back wall like this is a defect. Okay. But in this case, we do not have the back wall, because the back wall signal is not going to come, since it is going to go in a zigzag manner like this. Okay. So, So, that means for weld inspection, where you do it by angle probe, you need to find some other reference which can be used like the back wall signal. Okay. So, let us see in this case what is that reference that we can use to characterize defects and find out the defect echo on the display. So, this is the incident angle and it will hit the back wall and then again go back to the top surface. So, this point when it is coming back to the top surface again is known as a node. So, this is the first node and then you will be having second, third and so on. Okay. So, the distance between this first node and the probe is known as skip distance. Okay. So, this point where it hits the back wall, that is half of it. So, that is half skip. Okay. And if the thickness of the sample, if it is T, then you could see that this, if we call this skip distance as Sk. So, you could see this Sk by 2, which is this distance by T is equal to tan theta, which gives you the skip distance as 2 T tan theta. Okay. So, this is how you can find out for a given thickness and for a given beam angle what will be the skip distance. Okay. So, what you need to do in case of inspecting a weld is to keep this probe at half skip, and when you do that you could see that it will go all the way to the bottom of the weld, and then you have to move it to full skip, because when you move it to full skip from half skip, then it will go all the way to the top. Okay. So, if you see it in case of the weld, let us say the weld is like this. So, when you keep it at half skip, then this will go all the way to the down and this will hit the root. Okay. And then when you move it to the full skip, then it will go all the way to the top. Okay. So, since you need to inspect the entire weld from the root to the crown, so this is your root and this is the crown or the top, you need to move it from half skip to full skip, because as you could see when you move it from half skip to full skip, it is going from bottom to all the way to the up. Okay. So, if you are somewhere in between here, then it will go to somewhere in between into the weld, and if there is any defect, then at that defect interface, this will reverse the direction as I said before, and then it will come back to the probe. Okay. So, that is why in this case first of all the reference is the half skip, and you need to move the probe from half skip to full skip, so that you can cover the entire weld from the root to the crown. Okay. So, when you do the inspection, this is how you need to move the probe. So, let us say this is the weld that you have over here. Okay, so, this weld you are going to inspect, and you need to keep that probe first at the half skip. So, then it will go to the root, and then you have to move it to full skip as you do the inspection. Okay. So, for the entire weld you need to do this, you need to move in this fashion, you have to move from half to full and like this. Okay. It may not be the exact skip distance, but you need to ensure that you are covering a distance which is from half to full skip distance. So, you need to move your probe that way as I showed this particular diagram, so that you do not miss out on any portion of the weld. Okay. If you do this moving the probe from half skip to full skip, you will be covering the entire weld as I said from top to the bottom. Okay. So, this is how you should do a weld inspection by using ultrasonic angle probes, and in this case your reference will be half skip. For example, if you have any defect near the root, you can see it with respect to the half skip. Let me show you that. Okay, so, this root has a particular round kind of shape, and let us say the root diameter is d, okay. And if you keep the probe at half skip, then this will go to the root. Okay. And you will see on the display, you will see a signal like this. So, here also the first thing that you see is the initial pulse, and then you will have the half skip distance. That distance is known for a given angle and a thickness, and in this case you would see since it is going all the way to the half skip, you will see the echo from the root at the half skip. In this fashion. Okay. So, that means this particular distance is the root diameter d. Okay. So, this is how in case of weld inspection by angle beam probes, the reference will be the half skip. Let us say for example, if you have a defect, let us say you have some kind of root cut or lack of fusion, due to which there is some improper fusion between the plates, and at the root there is a opening like this. So, in that case, if you keep your probe again at the half skip, so even before it goes to the root, it will encounter this defect, okay, because there is now an opening. And now, if you see the display, your initial pulse and the half skip, and it will appear before the half skip, because now although you have kept it at half skip distance, but it is not going all the way to the root, since there is a defect over here, an opening over here. So, it is stopping, it is encountering that interface which is before the root, and then it is going back to the probe, and that is why you will see this defect echo coming just before the half skip. Okay. You can confirm it with that whether it is a root cut or a lack of fusion kind of defect. If you move this a bit to, let us say, a new position like this. Okay. So, in that case, this will also move closer to the half skip. So, if the first position was 1 and then you have moved it to 2, then this is corresponding to 1 and this will be corresponding to 2. Okay. So, by moving this, you can confirm that at the root there is an opening or there is a defect, due to which you see this echo coming before the half skip, and as you move little bit away from half skip distance, this echo is also moving towards the half skip. Okay. So, this is how the half skip distance acts as a reference in case of weld inspection. Okay. So, if you have any defect or something into the weld, let us say over here or over here inside the weld, if you have any defect, then when you keep it in the half skip, it goes to the root, and then as you move away from the half skip, let us say in between half skip and full skip, if you keep it, then it can go and encounter these defects which is inside the weld, and the moment it encounters this defect interface, as I have said before, this will reverse the direction and come back to the probe, and that is how you will see the defect echo with respect to the half skip distance. So, the defect echo now should appear after the half skip, because in this case, as you would have seen here, this distance is more than half skip. So, in order to get a signal from the defects which are inside the weld or which are in between the top and the bottom of the weld, then you have to keep the probe more than half skip, and that is how the defect will appear after the half skip in this fashion. Okay. So, this is how the half skip distance will serve as a reference for inspection of welds by ultrasonic testing. Right. So, now we will see some more applications of this particular technique, and then we can close this chapter. Weld inspection we have just now seen, but this can also be applied for castings, for defects like blowholes, cracks, tears, shrinkage. So, these are the most commonly occurring casting defects, inclusions, etc. Okay. But ultrasonic testing is most suitable for mill products which are given some kind of shape by a metal forming process like rolling, forging, extrusion and so on. So, these are called the milled product. So, the defects that you encounter during these metal forming processes such as rolling, forging and extrusion, those kind of defects can be easily inspected by ultrasonic testing. For example, in rolling, like you can have this kind of products, sheets, then plates, strips, okay, and there are different kinds of rolling defects which can be inspected. Similarly, in extrusion also the kind of extrusion defects that one encounters, those can be inspected by ultrasonic testing. Welding we have already seen. So, these are the kind of welding defects. That can be found out by this ultrasonic technique. Cracks and so on. Okay. Then bonded joints also to find out the soundness of the joint, whether the joint is good or not. There again ultrasonic testing is very useful, like if you have this braced or soldered bracing or soldering joints, or adhesive bonding. So, in all these cases, in order to find out whether this bonding is good or not, the soundness of the bonding, whether it is good or not, ultrasonic testing can be utilized. Okay. So, these are some of the applications of the technique. There are many more, but these are some of them. So, this will bring us to the end of this particular technique. And before we close this chapter, let us summarize and see what all we have learned for this particular technique. So, first we learned about the basic nature of ultrasonic waves, and then we saw different types of waves like longitudinal and transverse or shear. Then we went on to see the basic principle of this particular technique, which is echo or reflection of sound waves from an interface, which could be the discontinuity or the defect itself. Okay. So, then we talked about something called mode conversion. When you send the waves at an incident angle, a part of the longitudinal wave can convert into shear wave. And then I told you that if you want to do ultrasonic inspection by using angle beam, then it is better to exclude the longitudinal wave and keep the shear wave, and for that we saw that the incident angle has to be between the first critical angle and the second critical angle. And we derive this first critical and second critical angle based upon Snell's law. And then we learned about different types of transducers and the construction of the transducers. So, we learned about two types. One was piezoelectric transducers, which are also known as electroacoustic, and then we have seen one more type which are known as EMAT or electromagnetic acoustic transducer. So, in this case we saw that you need a couplant to exclude the air gap between the probe and the sample surface, and in this case we saw that in this EMET probes you do not really need couplant, it is a couplant free operation. Okay. Before that we also learned about the beam shape which depends on this particular ratio lambda by d, wherein lambda is the wavelength of the sound waves and d is the size of the transducer. And then we saw that for all practical purposes, for all practical cases in wherein the d is much larger than lambda, the beam becomes directional and takes up a shape which resembles kind of a searchlight. Okay. Then we talked about a very important aspect of ultrasonic testing, which is calibration, and then we learned how distance and area calibration are done. Okay. And in this we have also seen how the angle probes are calibrated using the IIW reference block. Okay. So, these are the different aspects that we have learned about this particular technique, and with this we can close this particular chapter. So, I am going to stop here today. I will see you next time with a new topic. Till then, bye bye and take care.